In this module, we will consider oscillatory motion. Any single object or collection of objects that are in a stable equilibrium configuration will experience oscillatory motion if perturbed slightly away from equilibrium. If we assume that conservative forces are holding an object in equilibrium, then we imagine the object to be at a local minimum in the potential energy diagram for the object. This picture is very generic and is applied across essentially every branch of physics. So, understanding oscillatory motions is extremely important for understanding the physical world. The most basic and widely applied form of oscillatory motion is simple harmonic motion, abbreviated SHM. It represents perfectly periodic motion of something. Simple harmonic motion never really exists macroscopically in nature. Oscillations are either damped away or some driving force excites them. But damping is often very small, and simple harmonic motion is often a very good approximation. Perfectly periodic motion is characterized by the period t or frequency f of the periodic motion, and these are simply related as the period is equal to the inverse of the frequency. It turns out that it is more convenient to represent periodic motion in terms of angular frequency, omega, which is related to the ordinary frequency by multiplying it by 2 pi. We've run into angular frequency before when we were considering rotational motion, and there is in fact a very deep connection between periodic motion and rotational motion. While simple harmonic motion is seen in a wide range of systems, its mathematical description is always the same. X is equal to a cosine omega t plus phi. Here, omega is angular frequency. It encodes the information about the period t of the periodic oscillations. Phi is a phase constant. It determines the phase of the system at t equals 0. Together, omega t plus phi give us the phase of the system. It's the argument of the cosine function, and it specifies the phase of the system at time t. X represents the displacement of the system. It's the deviation away from equilibrium. This can have different units depending on what is being modeled, but is often simply representing the linear distance by which an oscillator has deviated away from its equilibrium position. And A is the amplitude of the oscillations, that is, the magnitude of the maximum displacement. The amplitude and the displacement will have the same units. Now, let's assume that x represents a linear displacement, and consider taking two time derivatives of the equation for simple harmonic motion. Our first time derivative will then give us the velocity. This will be equal to minus omega a times sine of omega t plus phi. Taking a second time derivative gives us minus omega squared a cosine omega t plus phi. But a cosine omega t plus phi, that's just our displacement, so we can write the second time derivative of the displacement in terms of minus omega squared times the displacement. We arrive then at a fundamental relationship for all objects which undergo simple harmonic motion. This equation is called the harmonic oscillator equation. Mathematically, it's what's called an ordinary differential equation. You don't have to understand exactly how we solve these equations right now, but it is important to understand that all systems undergoing simple harmonic motion will satisfy this equation. You need three pieces of information to completely characterize simple harmonic motion. Most directly, if you know the angular frequency, the phase constant, and the amplitude, then you know the displacement as a function of time. But any other three distinct pieces of information about the oscillator will suffice. For example, if you know the period t, along with the initial position and initial velocity, then we also have enough information to completely characterize simple harmonic motion for that system. We can easily obtain the angular velocity from the period. We can also determine the phase constant and amplitude from the equations relating them to the initial position and velocity. Taking the ratio of the initial velocity to the initial position yields an equation for tangent phi. Squaring the equations for both initial position and velocity, and using the identity that sine squared phi plus cosine squared phi equals 1, we can isolate the amplitude. It is important to remember that given tangent phi, it can be a bit tricky to correctly determine phi itself. The best way to do this correctly is to draw a diagram similar to the unit circle diagram from trigonometry. In this case, while we simply let x be represented on the x-axis, the y-axis will represent minus v over omega. Now, the position and velocity of the oscillator will always fall on a circular path of radius a in this diagram. The angular position of the oscillator on this circle is the phase of the oscillator. Knowing the initial position and velocity then gives us the phase constant phi. Let's explore the phase of the system a little more deeply. The phase of a simple harmonic oscillator is simply a value in the range between 0 and 2 pi radians. This may seem a bit confusing since omega t plus phi can take on essentially any value depending on what value t has. If you want to plot the oscillations as a function of time, this is perfectly reasonable. But because the oscillations are periodic, describing the phase of the system in terms of this total phase does not make the phase of the system as clear as it can be. Therefore, we subtract some integer multiple of 2 pi from the total phase to get the phase in the range from 0 to 2 pi. Mathematically, this is giving the phase modulo 2 pi. A phase of 0 radians means that the oscillator is at its maximum positive displacement. On this diagram, we have labeled one particular peak here as the maximum possible displacement and has phase of 0, but any of the peaks would equally well be representative of a phase of 0 radians. A phase of pi over 2 occurs when the oscillator has vanishing displacement and maximum negative velocity. A phase of pi radians means the oscillator has a maximum negative displacement, and a phase of 3 pi over 2 radians means that we have, again, vanishing displacement, but in this case, a maximum positive velocity. The phase constant, little phi, is the value of the phase at t equals 0. For this plot, we have chosen a value for the phase constant of 1 radian. Since oscillations occur around a stable equilibrium point in some potential energy, it is useful to consider the mechanical energy of the oscillator. If there is no friction or other mechanism for energy loss, mechanical energy will be conserved. In general, oscillatory motion occurs when a system repeatedly cycles its energy between potential and kinetic energy. An oscillator will have its maximum kinetic energy when it is at the stable equilibrium point, and its maximum potential energy when it is at a turning point where the kinetic energy goes to 0. The simplest example of simple harmonic motion is the motion of a mass m attached to a spring of force constant k. The spring will obey Hooke's law, which says that the force exerted by the spring on the mass is proportional to the deviation of the spring away from its equilibrium position. To make things simple, let's consider putting the equilibrium position of the mass at x equals 0. We see then that the force exerted on the mass will be given by minus kx, which is, of course, equal to mass times acceleration of the mass. And, of course, we can write the acceleration of the mass as the second time derivative of its position. This means that we can easily write the second time derivative of position as minus the force constant k divided by the mass m times the position x. And we know from the harmonic oscillator equation that this is also equal to minus omega squared x. And this gives us a way to immediately determine the angular frequency of a mass on a spring, and it's given by the square root of the force constant divided by the mass attached to the spring. Now let's consider the energy stored in our mass attached to the spring and undergoing some oscillations. We begin with the equation for the position and the velocity of our oscillator, and now we consider the potential energy of a spring. That's given by 1/2 k x squared, and if we replace x by the harmonic oscillator version of its position, we find that the potential energy of the mass on the spring is 1/2 k a squared times cosine squared of omega t plus phi. Similarly, the kinetic energy of the mass on the spring is going to be given by 1/2 mv squared, and replacing v by its harmonic oscillator version, we get 1/2 m omega squared a squared sine squared of omega t plus phi. Now, consider the phase of the system such that the cosine is plus or minus 1 at that position. That means that the sine at that phase will be 0, and therefore the energy of the system will be given entirely by the potential energy of the system, and we find that the energy of the system is 1/2 k a squared. Similarly, when the phase of the system is such that the sine will be plus or minus 1, then the cosine will be 0, and the kinetic energy will be all of the energy of the system, which is going to be 1/2 m omega squared a squared. Notice that these two versions of the total energy of the system are equivalent because of the relationship between the angular frequency omega and K and M. And also notice that the total energy of the system for a simple harmonic oscillator is a constant. It's independent of time. Of course, macroscopic oscillators are not perfect and always have some form of dissipation removing energy from the system. The loss of energy does not affect the frequency of the oscillations, but it does cause the amplitude of the system to decrease with time. The kind of oscillations you get depend on how rapidly energy is dissipated. For underdamped systems, oscillations will pass through the equilibrium position at least once. For overdamped oscillations, the oscillator never passes through the equilibrium position. And for a critically damped oscillator, the oscillator approaches the equilibrium position as fast as possible, but without ever passing through the equilibrium position. Critical damping represents the special case that occurs at the boundary between underdamped and overdamped oscillations. Macroscopic oscillators can maintain their oscillation in the presence of dissipation only if some mechanism adds energy back into the system. For a force to add energy to an oscillator, the force must itself be periodic and act with the correct frequency and phase. If the frequency or phase is wrong, the force will sometimes remove energy instead of adding it. The optimal frequency for adding energy to a system is called the resonant frequency.